Hey guys, I don't know if you want to rock or not, but today we're going to talk about rocks and geology and the earth and all sorts of groovy things. So hang on and let's see what happens. First thing you should know is that rocks are made of minerals. Minerals are chemical compounds. Right here you see a picture of quartz or a diagram of quartz. You've got a silicon atom in the middle of this thing, and then you've got 4 oxygen atoms that surround that. And SiO4 quartz there is, I think, the second most common substance in the crust of the earth. There's lots of other minerals too. You can see here we've got quartz and feldspar and mica, amidol, olivine, calcite. They can make all sorts of structures, and they make these structures because these little things can snap together and make different shapes. It's a little bit like Legos where you can put them together and make different stuff with it. You can make chains, long chains. They can be by themselves, bow ties, rings that build up into columns, sheets, all sorts of shapes. And you can see some of those here. Here's some columns that are built up, and different structures and stuff. You may know that mica comes in sheets, so that typically is more of a sheet structure. But the minerals are really interesting. When you pick up a rock, it could be made of one of these minerals or a whole bunch of these minerals, depending on what's in there, what it's made of, and its history. You've got 3 main choices of rocks here. Once you've taken these minerals, you could make rock 3 different ways. Those 3 ways are igneous rock, metamorphic rock, and sedimentary rock. I'm sure you've heard of those before. And there's really maybe one other here, the magma. Magma is molten rock. So down deep in the earth, and I've got a diagram of this, the outer core of the earth is liquid, molten rock. It's very hot. If it were on the surface of the earth, we would call it lava. But once, while it's down in the middle of the earth, we refer to it as magma. Well, at some point, everything was magma, and it came to the surface or close enough to the surface to cool off. And as it cooled here, it turned into igneous rock. Well, if igneous rock were to melt again, it would be magma again, and it could turn back into igneous rock. Or maybe I take an igneous rock and I apply lots and lots of heat and pressure, and that heat and pressure changes it, makes it into a metamorphic rock. A metamorphic rock could melt, turn into magma, which would cool into igneous rock. Maybe the igneous rock weathers and erodes away, turns into sediment. That sediment could be sand or dust. It could be pieces of inclusions and all sorts of things that we'll talk about here. But if that gets compacted and cemented together, if it gets glued together, all of that, a whole bunch of sand could get stuck together and could make a sedimentary rock called sandstone. And then that could weather back down into sediment and remake sedimentary rock. Heat and pressure would turn it into a metamorphic rock, which could weather. You get the idea. Anything can become anything else through the main processes. Melting, it results in magma. Weathering and erosion ends up in sediment, which can get compacted and cemented together to make sedimentary rock. Heat and pressure changes the nature of rocks. Kind of like if you put some biscuits in the oven and you leave them too long, right? They're going to get real hard and darker, right? Same kind of thing happens here. If you take a sedimentary rock and you bake it too long, if it's up in near the magma where that heat is cooking it at tremendous pressures, then you can end up with a metamorphic rock. So that's the rock cycle there, and we'll be seeing more of that. I wanted to talk a little bit about each one of these 3 kinds and show you some examples and some traits. Igneous rock is rock, we said, that was formed by cooling molten magma. Here you see a bunch of different ones, and this is the easiest one to tell here. Obsidian is that black glassy looking rock. You can see the volcano off there up in the top corner, that magma becoming lava as it shoots to the surface of the earth. There's lots of pressure that's pushing it, and that river of molten rock is going to flow downhill, and it's cooling off the whole way. It's giving off that heat to the to the air and to the ground, and if it goes into the water, those would all cool at different rates, right? Things that cool very quickly are going to turn glassy. Things, if they're still underground but they're cooling off underground, can turn into granite or lots of other igneous rocks. And I've got a little table here, but you see they can be different colors and different textures and different all sorts of things. So on this picture here, I've got the minerals up at the top. Those are the main minerals that make up igneous rock, and of course I've got the igneous rocks down here. So I could take some quartz and muscovite and case bar and mix it up and end up with granite, say. There's a couple granites on here. Here in South Carolina we have something called blue granite. It's got extra minerals in it that give it a distinctive South Carolina blue color. There's that obsidian, that black glassy rock. So lots of interesting rocks that can be made through an igneous process. Right here, I got a little diagram of the volcano. Since we're talking about igneous rock, igneous means fire. You've got all that molten magma down here. This would be referred to as a magma chamber. And down deep in the earth, you've got that. If there's a crack, then lava can flow up it. And you can see here where lava has flowed up into this and made what's called a, well, this is the main vent here. And then these things, shoot, I forgot the name. But usually on a volcano, there's a crater there where pressure and that magma shooting out has carried away material. And so there's a little bit of a drop right there. And then if the pressure gets high enough, if there's an opening to the surface and the pressure pushes all that magma, it's going to come out, be lava up here. It throws off a whole lot of ash and rock and debris, and so volcanoes are pretty interesting. When I was in middle school, there was a Mount St. Helens that went off. I've got a picture here coming up. That was a long time ago. So we haven't had a whole lot of volcanoes in this country go off. If one goes off, it's probably going to be in Hawaii. There's always volcanoes going off, but I don't know of any in the continental United States lately. Maybe since Mount St. Helens. Maybe I'm crazy, but if another one goes off in the next little bit, everybody's kind of watching Yellowstone. There's a big possibility there sometime, in the next 10,000 years or some one of those kind of things. But it could go. Who knows? Anyway, volcanoes are interesting. That's the source of all that heat and pressure. If this is the magma chamber here, then you could see how this area right here would be heated by all of that magma. That's where you would get your metamorphic rocks. You can see the layer structure here. So maybe this was sedimentary rock, but now it's being baked and turning into metamorphic. Here's that picture I promised you of Mount St. Helens. 1980, in May, it was starting to rumble. The earthquake detectors, the seismographs were, saying, hey, something's going on. And those are kind of some of the indications. There's smoke. There was a little bit of sputtering up there, if you will. But when this thing blew in 1980, it was equal to the energy of 10 million tons of dynamite. There were 63 people that were killed, billions of dollars of damage, 200 homes, 185 square miles destroyed, entire forest just blown down. You got a time-lapse photo here. This is number one right here, where not much is happening, a little bit of smoke and a little bit of stuff. It starts to go off, and then you can see that it actually blew out the whole side of the mountain right here. That's one of these right here where the vent led to a place right there, and there was enough pressure just to kind of blow out the edge of that thing. And like I say, I've already forgotten what that's called. I apologize. The little map up here in the corner is an ash map. It shows where the ash was, where it went. And you can see there's three colors. It's not real big, but red is right around the volcano. They got a super heavy layer of all this dust and debris that you see here. The orange, the wind blew that ash kind of eastwardly, and made the orange path. But even the yellow right here spread all the way out over there and came down here. And other places had a light dusting. I can remember going out to the car after Mount St. Helens, and there was just a little fine layer of dust on everything. Nothing to, worry about everything. But I mean, it was a big deal. And when one of these things goes off, it can change the weather. You're not going to get the sunshine, so it cools off, and just all sorts of things. Here's an interesting picture. If you drive down to Atlanta, eastern Atlanta, and there's a place called Stone Mountain. Somebody carved some people in it for some reason. But here, this magma chamber up under the earth has found a way to either uplift here to push, and kind of lift all that, the lighter layers of soil there and make a little pocket there, or it found an empty place and came up and filled that. And then these pockets up here cooled off and turned into rock, into igneous rock. And then over thousands of years, all of this top surface here was worn away through erosion. So you get wind and rain and everything beating on it, and it just strips away all that, and you're left with this solid chunk of rock that you see here. And you can go down there and climb up the up Stone Mountain. There's a cable car if you're lazy, but whatever. It's down there. Here's something about sedimentary rocks. Remember again that sedimentary rocks were formed by layers of sediment. In this picture right here, you're looking at a mountain, but can you see the layer structure there? Anytime you see that, you know that that's layers that have been laid down. So, and I'll show you some of those processes, but let's say that a river washes and cuts the banks down. It's removing dirt as it goes. Well, it's going to dump that dirt when the water slows back down, and you might get a big flood that puts down a layer of mud and silt and sand, and then a year later or 6 years later, you get another layer, and layers and layers and layers build up. And that's what you're seeing there. Anytime you see those layers, you know that there's a sedimentary process going on. I didn't put the minerals this time simply because they're the same minerals they were last time. The minerals that make up igneous rocks are also the minerals that make up sedimentary rocks. But the rocks look different here. You can see that they're, if you could feel it, they're generally softer. They're not as hard, not as angular, and you're not as likely to see those crystals gleaming in them like you do in igneous rock. Sandstone, limestone, there's a couple different kinds of limestone here. Siltstone, sand washed down and made up layers and got glued together. Siltstone, it was silt that laid in. Oil, shale. These oil shale is something that we investigate for deriving a little bit of petroleum, gasoline out of, and the fracking process, I believe, kind of goes after some of that. They break the rock and extract it, and not a super good idea, but it's what they do. Coal is a sedimentary rock. It has organic matter that's in there, plant matter, and leaves and layers of stuff. All of that trapped plant energy is still in there, and that's why we can burn coal and get that energy back out. Chalk is a sedimentary rock. So lots and lots of those to kind of think about. Talking about the weathering and the erosion side of this, here again, you can see the layer structure. So this was built up over thousands of years. Even if each one of those was 1 year, let's say it flooded every spring, and made a new layer, kind of like trees. You could go back and count how many layers there were, and start thinking about how long it took to make that. But this has all been worn away right here. You can see that the rain and the wind and the ice has gotten in between the cracks of the rock, and when it freezes, it expands and breaks that. And now I've got smaller rocks, and those eventually fall down. And I don't know if you can see it in this picture, but right here, there's like a layer of dirt, sand, sediment, if you will. So it's kind of being cut away from up here and going down here, and the rain will wash it into the gullies and into the creeks and the rivers. It'll be carried somewhere else, and eventually will make new layers, could make new sedimentary rock if it gets cemented together. So that's kind of neat. Here's some pictures of streams. You can see that the fast-moving water here is removing sand and silt and rock and carrying stuff with it. But when the creek slows down, it's dumping all of that. It doesn't have enough energy to carry it anymore, so it just drops it, and that stuff builds up. The wind and the waves cut rock away. Here, this is kind of an interesting picture. You can see that the topsoil is getting stripped away, except for where these little plants are kind of holding on. The root system is going in there and holding that little bunch of dirt together, but everything that didn't have the root structure has gotten blown away and will continue to blow away. So, you know, here in the South, somebody said, roots do a good job at holding soil together, and the erosion was so bad that they felt like they had to do something, and they went and planted kudzu, and we all know how that turned out, but they were trying to hold on to the soil so it didn't all wash away. Not saying it was a good idea, but that was the thought. Right here, the waves have just beat on this rock until, you know, there's a tunnel through there. There's a cave, kind of open cave, I guess, but you could have a cave, you know, from these things. At the bottom of rivers, we call that a delta. The Mississippi Delta is there at the bottom of the Mississippi River, and it fans out like you see right here. So that fast-moving water picked up silt and sand up in, you know, Illinois or whatever, and it carried it down river through Tennessee, Memphis, and New Orleans, whatever. But when it slows down, it's going to dump all that out, and it's going to make these alluvial fans here. Right here you see at the bottom of a mountain, rainwater, snow melt has run down the mountain, and it's picked up some dirt and sand and it's dumped it all there at the bottom. So that's another geologic process that changes where these minerals are and changes the structure of them to where, you know, it wears them away and makes something new out of them. So that's kind of neat. Let's talk about metamorphic rocks. Again, these are ones that have been changed by tremendous heat and pressure deep in the earth. Here's a magma chamber, lots of heat, lots of pressure. Here's all this rock around it. You've got some rocks here in the kind of floating on the surface of this, and depending on what the minerals are and the things, you know, less dense things are going to float, so they could just be floating there. They could be stuck in the wall and just getting superheated, not quite melted. But you know, if you heat granite, you get schist. If you heat a shale, I believe, you get slate, and quartz turns into marble, and I don't remember all of the things here. Check out this one right here. This is called gneiss, and see how there's a layer structure there, but that layer is warped. It's bent. Well, the layer structure came from a sedimentary process. So this was originally a sedimentary rock, but the pressure, the motion of the earth lifting and twisting things has twisted those layers, and then the heat and the pressure has made that into a metamorphic rock. So you can see the layer structure. It started out sedimentary, it went metamorphic. This, on the other hand, was an igneous rock that became a metamorphic rock. So just lots of possibilities. How are you supposed to keep up with all that? Well, geologists have a rock key, a little table that they look at, and they start asking themselves questions. And I've got three here that we could look at real quick. This one on top here is gray. You might not be able to see it, but there's some layer structure on the side. It's kind of a dull gray. And the first question is, can you see little flashes of light or not? Now this one down here, you can see all kind of shine coming off of it. But with this rock at the top, if I were trying to figure out what it would, I would start here and say, no, I don't see any flashes, but I do see layers. So that means it was made of sediment. So either it's going to go off this way or it's going to go off this way. And you see how you just kind of keep asking these questions. Does it shine? Are there layers? Is it squished, fine, grain, or dull? Is it lightweight and made of dark organic? If that, that would be coal. That doesn't quite look like coal. Coal is black. This isn't black. It's not dark organic. It won't burn. It's a rock. So we wouldn't go that way. It's definitely made of sediment, but it's not shale, mud, it's not sandstone and everything. This is actually a piece of slate right there. It's just been squished flat. And people for hundreds of years have made slate roofs. It's such a layer structure that you can break it into those layers and make little thin sheets of it and use it for like shingles to shingle the roof of your house with and stuff. So that's an example of slate. Looking at this second rock, very clear lines there. So it's a pretty good bet that that is a sedimentary rock. Starting in the middle again, I don't see a flash, so I would come down. If it didn't have layers, I'd head off this way, but there clearly are layers. So, but it's not, fine-grained and dull. It's not coal. It's made of a sediment. So here's some choices. Could be made out of mud and be shale. It's actually sand. If you were to pick this rock up, you could feel that it feels sandy. It feels gritty like sand. And if you rub it a little bit, sand will actually usually flake off, and you can feel that and know that you have a rock that is, not very hard, not very strongly glued together. It's just kind of compacted and cemented. And if it's starting off with sand, then you're going to have sandstone, which is what you got there. One more here, glassy, shiny rock. I think you already know what this is, but let's follow the key here. You start, it's got shine, it's got flash. Is it glassy? Yeah, definitely. So that's an obsidian there. But you can see, does it have crystal faces? It's not faces, it's not like, you know how a diamond has faces to it, flat surfaces. Some of those have been polished and cut special. But, then I would come up here and say, well, there's a crystal structure, and it might be basalt, or if I get up here, it's granite or something. It takes a long time to get used to using that. I am not a geologist. I have not been, trained for years on this, but I do find it interesting, and just knowing that there is a rock key that kind of helps guide you through that is a good thing to know. And you can get a much better rock key than this. This just happened to fit on my screen. Here's another tool you can use. How hard is the rock? We said that sandstone was pretty wimpy and would just kind of, come apart as you rub it. Diamond, though, is very hard. And this guy named Mo came up with a scale 1 to 10 on how hard the rock is. Talc and gypsum, those are very soft, 1 and 2. You can see it goes up like that. Quartz is about a 7. So when you find a quartz rock, that's pretty hard, but not as hard as diamond or corundum or topaz. You could actually take a diamond and you could scratch the quartz with it. So that's a trick that people do here too. They'll carry around a handful of items, and if a copper penny, which has a hardness on this scale of about 3.5, will scratch it, then it's got to be calcite or gypsum or talc or something that's way down at the bottom of the scale. On the other hand, if you pick up a piece of fluorite, which has a hardness of 4, and can scratch the penny, then you know that, it's harder than a 3.5, so fluorite might be a good guess. Fluorite has this real interesting double pyramid shape to it. Sometimes it has that purple to it, and sometimes it doesn't. But quartz would definitely scratch the penny right there. A knife is, usually everybody should have a knife in their pocket, right? Or a piece of glass. Carry around a little piece of glass which has a hardness of 5.5, and you could nail down, is it in the bottom half or the top half of the list? Steel nail's a little bit harder than that. It's been hardened, so 6.5, and a drill bit's like 8.5 to 9. But a diamond would still scratch the drill bit. You know what I'm saying? So that scale is pretty useful. Varieties, inclusions, stratigraphy, oh my. Here are some different forms of quartz, and we call those varieties. It basically boils down to what else is in the rock. It's all quartz, so it's all silicon 04 that is making this up. But right here you have just, white quartz, and here's yellow quartz and pink quartz and purple quartz, and um, there are different elements that are mixed in there to give you those different colors. I think iron, if you have lots of iron in the quartz, it makes it purple to make it amethyst. If you have, I believe it's aluminum, you end up with a pink quartz, a rose quartz. And of course, we can do things to rocks. We're part of this process too, right? We could put superheat and pressure on a rock. We could mix in dyes, and gemologists do all sorts of things to make rocks. Sometimes people use radiation, X-rays, um, to change the appearance of rocks. Sapphires and rubies are usually treated. They're not natural at all. They're made in they take a rock, but then they're treating it to make it a different color, or different shape or something. Inclusions are any kind of thing that is included in the rock. Right here in the middle, you can see, this is an interesting picture actually. I wish it was a little bit bigger. But you've got a layer structure going on. So there clearly was some sedimentary action and layers built up there. But it looks harder than that now. So I would guess that this is metamorphic rock. And then through the middle of this, it looks like lava flowed through there, but it was carrying these big chunks of other rock. The other rock are called inclusions. Anything that's included in there. This stone right here has picked up some stuff as it formed. That's an inclusion, these dark marks. Any kind of material that's in there that's not part of the regular rock, that's separate from it. It's not evenly mixed like, here's blue and white and maybe some black, but it's uniform like that. This is not uniform, right? This is doing one thing over here, and here's something totally different. It's a rock stuck in this other rock. It's included. Stratigraphy comes from the word strata, which means layers. And the idea with stratigraphy is that you can look at the layers and kind of work out what happened. In this picture right here, you can see that I've got a loose rock here, and then a B and a C, and this D kind of cuts through weird like that, and then E. So there's kind of 5 things that happened here. I've got this kind of rock. Deeper down, I have this kind of rock. And one of the primary rules of stratigraphy is that the deeper down you go, the older it is. So this, would have formed, and then something looks like sedimentary layers built up there on top, and then maybe that eroded, and so we've got dirt that was eroded from the sedimentary layers, and maybe this is metamorphic or igneous down here. But, and then this line came through. That used to be matched up, but this fault right here kind of sheared everything off, and it changed. So working out those layers, but again, the basic idea is deeper down is older. Also here, whenever you see an inclusion, the thing that was included has to be older than the rock around it, right? Otherwise, where would it have picked it up on this flow, going down the mountain or through the land, through the ground, or whatever happened here. So some interesting terms. A cleavage plane is a place where you could cut stones between the atomic structure there, between the molecular bonds that are forming that. And if you're interested in gemstones and shaping gemstones, then you know all about that. I don't know anything about it, but I can see from the picture here that maybe this bond isn't as strong as that one. So if you knew what you're doing, you could take a rock and cut it right there. You can see here how this razor blade has just been pushed into between those layers. I believe that's mica. I can't really see it. But this red dotted line is another cleavage plane, another place you could cut that rock. And most of these are rough sapphires here, but you can see that this one has been cut and shaped and turned into a pendant or something. Here's one that I think is shaped. These two definitely have, these two have been worked and, could go into a ring or a brooch or a hairpin or whatever people do these days. we learn where those cleavage planes are, and then can dress the rocks up. I don't think anybody's going to wear an uncut sapphire, in a ring or something. It would just look like a big funky rock, but we could turn it into something that people would covet and pay too much money for. All right. Talked a little bit about faults before. This is a picture of the San Andreas Fault right here out in California. It's a place where the earth is shifting. And you've got three kinds here. A normal fault means that this is being pushed up and the other is moving down. On a thrust fault, you can see it kind of goes the other way. Here you end up with a cliff, if you will. And here's kind of a backwards facing cliff where the thrust up part kind of goes on top of hangs out over the underlying layer. Strike slip fault is when one is going east and one's going west or north and south or something. You can see the damage that right there is a good example of a strike slip fault, because the road used to run continuously. This piece has moved to the right, this piece has moved to the left, like that. That's a problem. When these things move, when the earth moves, it can set up a whole lot of pressure and cause earthquakes. You could get an opening and you could get a magma vent. You could get a new volcano there. You certainly get a lot of damage to road work. If you had a water pipe, a sewage pipe, electrical lines, phone lines run through the ground there, you can see how it'd be hard pressed to keep that all working. But faults are interesting. They kind of bring us to earthquakes here, and earthquakes are interesting. We've had a whole bunch of them this year here in South Carolina. We've had small ones, mostly 2 and 3 on the Richter scale. I'm going to show you that in just a second. But there's two kinds of waves that come off here. One is a compressional or P wave, P for primary, and the first wave that comes through, this travels really fast through the ground. Then you have a shear wave or an S wave, S for secondary. So the first one that hits, the P wave, vibrates back and forth this way. It compresses the ground and shakes back and forth, whereas a secondary wave shakes it up and down. And like I say, this one travels faster. They can do enormous damage. They can knock down buildings and bridges and break gas lines, and that causes fires and all sorts of bad things. So earthquakes aren't a laughing matter, but we've been pretty lucky so far. I've got a picture here, several things here. This is called a seismograph, and it makes a piece of paper called a seismogram. And the seismogram is a piece of graph paper, and then there's a little pin that tracks along like this, and whenever the ground shakes, you record that, and then it kind of dies off, and then the secondary wave hits. So right here, this would be the primary wave, dies down, and the secondary wave hits. Well, we figured out that if you measure the time that it takes for the primary wave to go to the secondary wave, then that'll give you a real good estimate on how far away the earthquake's epicenter happened, how far it was to the center of the earthquake. So I've got, this was actually an earthquake back in, I forgot the year. I think I got it on here. Yeah, Loma Prieta, 1989 in California. 62 people killed, 3,000 injured, $7 billion in damage. If you remember back to 89, some of you definitely won't, but they had bridges stacked on top of bridges. The earthquake collapsed the top bridge onto the bottom bridge, and there were cars stuck in there for, you can see over here that sections of the bridge fell out, and some people were lucky enough to get their rig stopped, and others weren't, so it was a big deal. Imagine waking up and this is your front yard now. Honey, call the landscaper. That ain't gonna do it, is it? So how do you figure out where it happened, how big it is, how bad it was, everything? The first thing they do is they measure that PS time from the primary wave to the secondary wave. You can see that the scale here is already set up for you. So this is 0 seconds where the primary starts, and over here 72 seconds later, I get the secondary wave. So they've written PS equals 72 seconds. The amplitude is how high this thing shakes. So you can see here in Eureka, California, a lot more shaking going on than in Vegas and especially in Elko, Nevada. All right, those are those three cities right there. And just looking at the amplitude, how bad it shook, you can make a pretty good guess that, with 280 versus 100 versus 60, that the earthquake was somewhere closer to Eureka than Elko or Las Vegas. It's kind of like a campfire. The closer you stand to it, the hotter it is, right? So Eureka got it pretty bad up here, and then Las Vegas is pretty big, but Elko not much at all. So somewhere, around this area somewhere. Well, we'd like to do a little bit better than that. What we do is we get the 3 PS times, primary, secondary wave, 50 seconds down here, 64 seconds here. You can also see that, the closer it is, the closer it is, the shorter that PS time is. The farther away you get, the longer time is. So that's another indication right there. But we're going to use that 72 seconds and work out a little thing right here. You've got these 3 lines which show the magnitude and the amplitude. We got those off the seismogram, and these 3 lines track those 3 monitoring stations, those 3 seismogram, right? So I don't remember which color's which, but let's try Elko here. 72 seconds and 60 amplitude. If I go to 60 amplitude right there and go up through 72, what's happening here? Amplitude, I already forgot the numbers, I'm sorry. PS time 72, there's a part I left out to get the distance, and I don't have that for you, I'm sorry. But yeah, left that one out. I don't have that's math stuff. I just want you to see these charts. If the distance is, let's say the San Francisco one was the closest, so we'll put the Eureka, California. So here's that distance. You'd match it up with the amplitude right there. It's going to cross through this line, which is called the magnitude. The magnitude is how bad the earthquake was at the epicenter, at the point of those rocks moving against each other, getting hung up, and then breaking, releasing that pressure, that built up energy there. This is like a 7.1 on the Richter scale. That's what that middle line is called, and that's pretty bad. That's a big earthquake. Again, the ones in South Carolina out in Elgin that we've had are down 2, 3, something like that, maybe 3.5. So, and this is a logarithmic scale, so the higher up you go, it gets a lot worse, all right? But anyway, where those cross is what you're looking for to get the magnitude. How do you find the distance? Well, we worked out the distance. Here's the thing. This is what I wanted to show you. There's a little graph version. There's a formula too, but Eureka, California had a 50-second time between the secondary and the primary. So if I go up to 50 seconds and then come over, it tells me that 480 kilometers is the distance from Eureka to the epicenter. So all you got to do is say, well, here's Eureka. Let's draw a circle that's 450 kilometers around there. Looks like it's 488. I can't read these lines very well. But draw a 488 radius circle there. Elko had 72. So you come up to 72, that's up here. And it looks like that's about 700, 695. What you got, Elko is this city. So you come out 695 kilometers, you draw a circle. And then from Las Vegas, it was 625, makes the green circle. You can see that all 3 of them cross right there at the bottom of San Francisco area, down at the bottom of the bay and stuff. That's the epicenter of the earthquake, and that's how they find out where it was, and with that other chart, how big it was. So those are kind of neat. Hopefully we don't learn a whole lot more about earthquakes here in South Carolina. The earth is made up of layers. The surface, the part that we know and love, is called the crust. Kind of like the crust of the bread is that outside surface. The mantle right here is kind of a mix of rock and magma, and it's just kind of ooey gooey stuff. It's not hard and crusty like the crust, but it's not molten like the outer core is either. I meant to put some more things in here. This is liquid. This is all molten here. And the inner core actually is solid. It's made up mostly of nickel and iron. It's highly radioactive. That radioactivity keeps driving the heat to keep this outer core molten, liquid. And then you've got the mantle, which is kind of a mix of solid and liquid, and it's cooled off out here on the crust, and we can walk around and go to the beach and do our stuff, right? So it'd be nice to know those four right there. You can break it down into smaller divisions too, but that's four is enough stages there. Let me tell you a little bit about plate tectonics. The earth is made up of pieces of crust, and those pieces of crust can kind of move and shift against each other, rub against each other, if you will. Right here we are in North America, and there's a North American plate, kind of like a piece of crust that's sitting on the mantle, which is floating on the liquid core, the outer core, right? So that piece is just kind of floating on all that. South America has a plate. There's a Nazca plate right here. The Pacific plate is under most of the Pacific Ocean. You can see how this works. Eurasian kind of holds Europe and Asia to, gives it something to sit on. All of these red dots, though, are sites, common sites of earthquakes and or volcanoes. So where these plates bump up against each other, then you get a lot of pressure built up right there, and you're liable to get earthquakes. Or there's a vent that pops up through there and can make a volcano. Mount St. Helens is right there somewhere, right in that ring of those, and all the big mountains. Not all that's not the whole process there, but that's a part of it. Down here you have Hawaii and all these islands. Those are volcanic islands, and we had a new one pop up the other day. There was a volcano under the water that ejected enough lava to actually make a new piece of land, right? And so the volcanic islands along here, you've got the plates come together, magma works its way to the surface, gets ejected in a volcano and turns to lava, it turns to rock, builds another layer of rock on top of that. And as every time it erupts, you get a little bit higher, and someday it pops up out of the surface of the ocean, and they call it Hawaii or something. That's kind of neat. These plates, looking at them from the side, kind of look like this. So here is, this might be the Pacific plate and the North American plate over here. You can see that that mantle up underneath there, the liquid and this gooey solid, and then the crust on top of that. And interesting things happen when these move. Not only do we get earthquakes and volcanoes, and you can see some of the vents right there. There's a vent that goes to the top. It's a cinder cone volcano. You get stratovolcano. That would be a layered volcano. Right here, there's a volcano coming up in the ocean. That's one of those islands that we were talking about. Here it looks like the plate is going up underneath this other plate, right? That's called subduction. This one is being subducted or pushed under that. Right here, it could be going under, it could be uplifting, whatever, but it looks like the North American plate here is being lifted and even warped up. And remember that rock that we saw that had that pattern? It had the layers, so a lot of sedimentary action going on there. But now I've got this heat and the pressure and these plates moving, and they have enough force to actually warp all of that rock and to reform it into the wavy lines that you see there. So plates are pretty interesting. Looking at the ocean floors are pretty neat, because guess what? There's mountains and valleys down under the oceans as well. Looking here, Myrtle Beach would be about right there in Charleston, and you can see that red layer there represents the continental shelf. And so that's land. It's not very deep relative to the rest of the ocean. You certainly wouldn't want to walk down here, because if you've been to the beach, you know that you can't walk very far before you're up to your neck. But, 50, 100, 300 feet, something like that. And then it just kind of falls off, and you're down on the ocean floor here. But you can see there's higher parts, and mountains and ridges, and so lots of that. A lot of the geology that we have on land is also going on underwater, under the oceans, as you could be expected. A little picture here in the bottom, it's got a boat. They have a sonar system going, and so they're shining radar waves down. It's bouncing back up. They're getting that, and they're making images of what it looks like. If you've ever used a fish finder, you know that you can go buy a little box that sits in your boat, and as you move along over the water, it'll show you the depth of the water. It'll show you, oh, here's a whole bunch of, odd-shaped things floating in the water. I bet they're fish. I better throw my hook over line. It's the same kind of idea. These guys are actually towing a second one back here to get a little bit better sweep on it. But that's how all these are mapped out, and that's kind of neat. Well, that's actually what I had for you there. That's the end of what I wanted you to know about geology. Don't think that that's everything there is to know about it. Please don't think that I know everything there is to know about it. Again, I'm not a geologist at all, but I did want to put some of these ideas and terms in your head and get you started thinking about it. It's pretty neat stuff. So thanks for stopping by. Have a great day.